Hello, and thanks for coming. This is the third in a series on models, and in particular the Chris Murray model, which has gotten a lot of traction and has been referred to as a prominent model and is being quoted in lots of newspapers in terms of predicting that the pandemic will be less severe than we thought, or more severe than we thought, or our state's going to be spared, etc. The original title of the first one was All Models Are Wrong, Some Models Are Useful. And I still feel that that's a tried and true expression in statistics and biological modeling. But this one is All Models Are Wrong, Part 3, The Search for Spock. Okay, just I'm not going to do much with today's news. I'm going to jump right into evaluating the model, but I will point out that even though I'm going to be kind of flipped today and be a little bit snide about some of what I dislike about this model, because I think that they've been very cagey about the uncertainty in their model and how good it actually is. And this is just to remind us that people are dying, and it's important that if we're putting information out there, it has to be good. And if it's not good, or if it's preliminary, or if it's in a work in development, we shouldn't be calling 3 different press conferences and news releases and doing interviews in the media and forgetting to mention that the model is still very much preliminary and has not yet been peer reviewed by anybody in the world. All right, so this is the much anticipated third installment of the trilogy. In the first 2 movies, our hero faced untold problems confronting the global pandemic from his study in San Diego, California, an alien in an inhospitable place. It's raining. And we're talking about the Chris Murray model, and it's named by that because it was referred to that by the White House. This is the main functional form of the Chris Murray model. As you can tell, it's quite straightforward. All we need to integrate is this exponential minus tau squared delta tau function with the 1 over 2 pi thing. That's the actual 3.14159 pi, but this p is something different. So once we figure this all out, we're in good shape, and it's going to be perfect. And so in our trilogy, I wanted to point out that we have a special guest star, Dr. Anthony Fauci, as he plays the younger Spock in the trilogy that we're doing right now. Okay, this is today's date, April 7th. UW model offers hope for Washington's coronavirus response, but still forecasts 82,000 dead nationwide. So Washington's estimate was much lower in this new round. I'm going to be comparing the predictions they made on April 2nd to the ones they made on April 5th, which, as you would suspect, is a 3-day difference. All right, so updated modeling from the University of Washington suggests the state has been effective at flattening the curve. This is in Washington, right? The UW's Institute for Health Metrics and Evaluation has created state-by-state projections of COVID-19 deaths, hospitalizations, and ventilator needs to help hospitals prepare as they move through different stages of the pandemic. In a news briefing, the Institute's director, Dr. Christopher middle letter Murray, said tweaks to the methodology and an influx of new case data have generated a rosier outlook for Washington state, though the model continues to estimate a nationwide death toll of around 92,000. In late March, the model indicated 1,400 people in Washington were likely to die. It also showed hospitalizations in the state would peak on April 19th with about 100 more patients than intensive care beds. Okay, I got major problems with this model, and I'm going to try to present them in an unbiased and professional manner, and I am fairly certain I will fail. But hopefully you'll see at the end of this why I am so outraged. All right, so my mom raised me right. She said always start with the positives, and so I'm going to start with the positives. So this model was developed by the Institute for Health Measuring Evaluation at the University of Washington. They've got a beautiful logo right here, a very nice slogan, measuring what matters. They got a beautiful picture of the coronavirus, which is an illustration I see everywhere, and their website is spectacular. It's gorgeous, and I'll show you some of that live, and we'll say, wow, that's really nice. Okay. They've gotten lots of press, so they have a press release from yesterday from the April 5th update, and today the April 6th update, and now they're modeling the deaths in all of the different countries of Europe. So they've solved the U.S. problem and the 50 states, so they've moved on to bigger and better things. They have links in their website to published articles, and it's really nice. We'll show you this in a second. And this is the image. It says COVID-19 publications. And as you scroll over it, the little green thing rolls up like a window shade going up instead of down. And then you click on it, and off you go to the publications. So let's see. And it has a great a searchable library of all the publications that have they produced on COVID-19. It can be filtered by document type, geography, and date. So you'll see that you can choose research articles or policy reports or geography. I've chose criteria and decalia. I don't even know what that is, and so forth. The problem is that at the end of the day, there are just two models, two papers total. The one where they published some information about the real-time case information on March 24th, where they're taking the Wuhan data and describing it epidemiologically, and it's published in a journal-ish, but it's mostly just data sources and how they sourced their data. And then the second publication, the one that's gotten all the press, this research article here from March 26th, which has been updated, I think 5 or 7 times since then. But the big updates were April 2nd and April 5th. When we go to the website, you'll see these beautiful graphics. What we're looking at here, for example, is a prediction of the course of the model through time, and we're looking at all the resources here, and we're showing in purple here the beds needed projected, and in darker purple the invasive ventilators, and green the ICU beds, and the dashed lines are their estimates, and then the shaded areas is the uncertainty in their estimate. And it's certainly very important to mention this uncertainty, because their model predicts 140,000 ventilators will be used now. I believe somewhere up here they said something about 140,000 ventilators. But notice that their variability at the peak goes from a low of 80,000 to a high of 280,000. So they could be off, they can be twice as high or half as big. So there's tremendous room there for uncertainty. And I don't think they've communicated that uncertainty at all well in their materials. They've said we've got 80,000, not 80,000, but the range is 30,000 to 200,000. That's a really different statement, isn't it? Okay, so I really only object to 2 specific things about this model. One is the way the model was presented to the press and the public as a well-established, validated, peer-reviewed, vetted model that's stable. And then, of course, the model itself. I do still like the website, so that's something. Okay, so if you Google Chris Murray model, you will get all sorts of things about the Chris Murray model being used over the last week and a half in all sorts of places, about how states will peak at different times, what the ventilator use is, and so forth. And it's really important that in these articles and in their own press material, they talk over and over again about this is a planning tool. This is different from the other models in that it's designed to help hospitals and states plan for when the pandemic is going to be worse and what kind of resources they're going to need in terms of beds and ventilators and so forth. So they care very much in this model about the state-by-state prediction, so that it's not just an aggregate, but they can actually be used for planning. It was interesting, as I was just happening to grab this, I noticed this 5 key facts not explained in the White House COVID model, and I thought, oh, maybe somebody else has some skepticism as well. So I looked up the article, and this was April 1st, so this was just 5 or 6 days ago. They talk about, for example, did Trump sort of change in tone from let's get out by Easter to April 30th, was that related to this model? And they said no. Officials implied the estimate was based on the administration's own in-house modeling, but it's actually the University of Washington's Institute for Health Metrics and Evaluation, or IHME. NPR contacted 2 researchers who helped put together IHME's model. We learned of some of the assumptions made by the model that the administration officials did not mention. Oh, and by the way, there's a 6th one that I'm going to get to that they don't use much data. Number 1, the president's guidelines have nothing to do with what's going on in their predictions. Their predictions are based on states' actions. They argue that in the model it's states that dictate social distancing and school closures and only essential work that drives this. Um, it assumes governors who, when they had built this model in late March or early April, hadn't issued statewide social distancing rules would do so within a week. It assumes that states will keep social distancing through June 1st, not April 30th, not May 15th, but June 1st. And it also points out that if we actually hunker down and get through this wave, that then 99% of us will still never have seen this novel coronavirus, and we will be susceptible to a separate second wave unless we do something different. And then, as I said, number 6, one that they didn't acknowledge, is the model is built on very scant data, incredibly few data points, and makes some really big assumptions in order to make those predictions. And I'll show you that it's clear that made a difference, that their predictions are unreliable. They're unstable. Okay, so they've published their article, right? Remember, they have 2 articles published from that big library that you could search? See, this is what I'm getting a little bit snide. The article they published isn't really a published article by any reasonable stretch. It's a non-peer-reviewed preprint server. And remember, I think I ranted on this at the end of number 2. This article is a preprint. It has not yet been peer-reviewed. And they go on and actually you can link and read more about that. And they say, this is the journal, that this is yet to be evaluated and so should not be used to guide clinical practice, and it also says in the broader One Health policy. So the journal that they posted their report in, which nobody else has looked at, says don't use to guide policy because nobody's really checked its guts. Okay, so I've talked about the publicity, I've talked about the beautiful website, but that I have all sorts of problems with the fact that there's not any true peer review and vetting. Now let's go to the model and I'll talk more about that. So it turns out I'm going to show you that there are really 2 different Chris-Murray models, the one that was published on April 2nd and the one that was published once they had a lot more data much, much later on April the 5th, 3 days later. They make dramatically different predictions. Yes, the aggregate total deaths is about 80 or 90,000 in both of them, but boy, oh boy, when you kind of open the hood and you look underneath, huge differences. So big, in fact, that they can't both be anywhere near correct. So one of those models is wrong. Absolutely frickin' got to be get dead straight wrong. Got it all wrong. So either the first model is right and they made it wrong, or the second model fixed what was wrong on the first model, or wait, if the first model needed fixing 3 days later, what makes us so confident that this model won't need fixing in 3 more days? Why should we trust even this model? Okay, so what's it's doing? It's predicting the epidemic in terms of the number of deaths as a sigmoidal function. It starts out at 0, and then it climbs sort of exponentially, and it's kind of steep, and then it kind of flattens out and hits an asymptote. Right? And there's just different mathematical functions that can do that, and they went and very specifically talked about the one they're using, the ERF error function, which is essentially the cumulative of the normal distribution. And by normal, I don't mean like typical, I mean the Gaussian normal curve that you may or may not have ever learned in statistics, but is really cool. It belongs to an exponential family of distributions that have this sort of term in it. It's really elegant, but numerically hard to integrate. So that's fine. So when you do these sorts of model estimations, you've got a bunch of parameters. You basically start the model off, and since you can't solve it like a quadratic, minus 2b plus or minus 4a squared over 2a kind of thing, there's no formula to solve it. You have to solve it numerically. So what do you run into? Well, you have parameters that have controlling how long it takes people to go through the ICU, or what proportion of individuals get sick, or how fast the virus spreads between communities. So you have all these different parameters in the model, and you start the model off and you let it rip, and sometimes if you're not careful, you'll get things like 108% survivorship over here, or minus 3% death over there. So you have to constrain your parameters to be within reasonable limits. So you can't have more than 100% survivorship or death and less than 0. So that's a huge thing. And they say since the form of their model is highly nonlinear, constraints are particularly useful to stabilize the numerical solutions. Now, that's not unusual and that doesn't make it wrong. But if the model's unstable and you have to kind of set the parameters in place where you want them to make it stable, then it's not so much of a model. And in fact, they talked about their optimization procedure. And so in these complicated models, they can take a lot of computational effort. And so you try to seed the original parameter values somewhere and have it sort of find the best model based on a bunch of criteria. And they argued that, in fact, it was very important that you seeded the model with that values were location specific and sort of appropriate for that area. So you have the Idaho starting conditions and the Ohio starting conditions and the Massachusetts starting conditions, because if you use a general starting conditions for all the states, they go all over the place. And so in a sense, that also suggests that the model does not easily converge on a stable prediction, but that it's highly sensitive. Okay, so let's just talk about a few things. So the shape of the function they're dealing with is, I think, a log normal distribution. And this is what a log normal distribution would look like. You would get a rise to a peak and a slower tail. So typically a log normal will have a steeper upside and then a slower sort of downside. And that's sort of what we expect in an epidemic. When it gets roaring, we get this just explosion of cases. And then it tails off, but more slowly, because it takes a long time for us to get all those, for those cases to go through the medical system, and also for us to really have lockdown seriously and significantly. So it usually takes some time over days as communities do that, so there's a slower decrease. This is the cumulative function. They're the same thing, except this is the deaths per day, if you want to think of it that way, and this is cumulative deaths till it's all over. That's what the model that they're fitting looks like. That's the functional form. This is the data they started with Wuhan City. So when they did the model on April 2nd, they had one and only one of these curves to use to parameterize their model, and it's Wuhan, which you can see makes exactly that same smooth rise to a peak and then drop off slowly that you expected here. Sarcasm. This is, and in the April 5th model, they made a very big point of saying we now have 7 sites that have just reached the peak or have gone over the peak. So now we can parameterize the model from a much larger set of observed epidemic paths, right? So that's great. 7's way better than 1. I don't remember them saying, by the way, this is all based on one and only one curve we've seen before, and it was noisy as all get out. But okay. So here's Tuscany in Italy, and you can see the smooth rise, and that you can clearly see the full part of the decrease toward, no, you can't. So they argue it's peaked, and that is high, not as high as that. It looked like it, and I don't know. And these are the other 4 sites in Spain and Italy. No, I think these are just the Italian sites. My bad. But you can see none of them are smooth. Some of them don't look like they've really come down much. So I have a real problem with this, because we're looking, the whole point of this model is if you can look at the shape of what's happening here and understand how it's rising, you can parameterize the family of curves it belongs to and predict where it peaks, when it peaks, and how fast it goes down, and how many total deaths there are. But if the real situation in any one city or region is way messier than that, do we believe that, the 7 points even anywhere near close enough? So I generated some perfect data, and these are log normal functions, and so I've got 3 family of 3 with different sets of parameters. So I would ask of you, okay, that's the data we have. Now it's perfectly smooth. What happens next, right? Do we have a sense? Well, it turns out that they have very different peaks and different lengths of time, but it's very hard to tell that from here, or here, or here. Now you can start to see it, right? So if you have lots of data on what happens, maybe you can use the slope and change in the slope here to figure out which of these many trajectories you're on, some which are shorter and fatter and some are tall, and because this would be a one where it peaks hard and fast and really overwhelms the medical system. This is one where it would be more flattened the curve kind of thing. And of course, the way they're modeling their function is as a cumulative distribution function. So this is the same set of models, and as you can see, they're eventually going to all asymptote somewhere. In mine, I had them all asymptote at the same overall total number of deaths, which is a simpler model, then they of course had that be a variable that they could parameterize. And again, where are these things going? And the answer is they cross all over the place, and it's not so simple. And little bits of variation down here in real data is going to make it very hard to tell which of these curves you're on. And that's why I think that the variability in the 7 data sets they draw from is so strong and so amazingly large, and the data we have is so variable in our state-to-state databases that it seems almost ludicrous to imagine this could possibly work, and it didn't. Okay, so we're going to look at some stuff. So they had a April 2nd release, and then they have an April 5th release. This is their PDF file that you can download that talks about what the major differences are between the model. It's more data, better models, and a growing evidence base. Having more timely, high-quality data is vital for the modeling endeavors. And so they talk about that, and they said thanks to everyone who helped out, and we have all the state-level data on hospital stuff. Because remember, this is a planning tool, so it should be used to plan for the next week or two where to position those very scant ventilators that we're arguing over that FEMA may or may not have. Luckily, they're publishing their technical appendices by Tuesday, April 7th. I looked at that about 20 minutes ago. It's not up yet. So let's go see if that... No. All right, so we'll go live. So let's look at the PDF itself. Wrong PDF. So this is the update that that they produced. I've actually marked it up a bit, so let me show that. Okay, so having timely information is important. They're going to publish an online thing, and this was updated on the 7th, and here's the estimates update page, which talks about Europe and doesn't actually have a technical appendix, and is what they posted yesterday. So they have not actually posted this technical appendix that I would love to read. Okay, so what's changed and why? Let's see. The table is this column April 2nd, this column April 5th. We think it's going to peak on the 16th in both models. Pretty good. Now, in our old model 3 days ago, old, we thought there would be 2,644 deaths at the peak. Now we think it's 3,130, a difference of 500. That's about a 20-25% increase. That's not small. And in terms of cumulative deaths through the first wave, we think it's going to be 81,000, not 93. That's down 11,000. So far, that 25% is a little worrisome, but this is looking good. Now, they made 4 substantial updates to the COVID-19 death model, and they summarized them. On March 26th, the only location where the number of daily deaths had already peaked was Wuhan City. So that was the basis of our estimation of the time from implementation of social distancing to the peak day of deaths. Since then, an additional 7 locations in Italy and Spain with large coronavirus epidemics have appeared to have reached the peak of daily deaths, and so forth. We now estimate the time from implementation of social distancing to the peak using all 8 locations. Okay, so there's the Man of La Mancha, Spain, and that's split across 2 pages. Not my fault. That's their PDF, not mine. Yeah, I would use a hard page return if I'm just silly that way. Those are some of the graphs I've already shown you. Wuhan is a really weird thing. It went up super fast. It had some weird stuff going on, and then blam, they clamped down. Now, I think they clamped down much harder than we did in the West, so I think that might have been steeper than we'll see here. I also have some suspicions about under and over reporting of data in China for political reasons. Okay, so they talk about school closures and how they do that stuff, and life is good, and we now use adaptive priors. So because the original model was so unstable, and there's going to be a method section for this someday, we actually kind of gave the model some constraints or some places to start about where they expected parameters might end up so that it would be more stable. And because of the first few days of new data was highly variable, we'd expect predictions would vary considerably from release to release. Now, I don't remember that in the Chris Murray model at the White House or in his press release saying, oh, by the way, I'm going to update this model every day or two, and it's going to vary wildly. So we really shouldn't trust any given day because it might be different the next day. That's certainly not what they said, right? So here's what's changed, and this is just mind-blowing, okay? So I don't know how long I've been prattling on, but I hope you've stayed with me. Okay, so hospital beds needed at peak April 2nd, 260,000, now 140. That's like a 50% drop. ICU beds, 40,000 to 30. Invasive ventilators, 30,000 to only 19,000. So 3 days later, they're like, nah, 30,000 ventilators is way too much. We only need 19,000 ventilators. Get real, dudes. So these are 30, 40, 50% changes in 3 days. That's a lot of change, and we're not done yet. We're not anywhere close to done. They looked at the hospitalization to death ratio, which I believe actually is the number of deaths per hospitalization upside down. So 4 hospitalizations to a death is 1 death for 4 hospitalizations. So in New York, 1 out of every 4 hospitalizations appears to lead to death, but in California, it's close to 1 out of 11. So there's a lot of uncertainty there that they're trying to incorporate. And here's where we get jiggy, okay? This is where it gets great. Time from hospital admission to discharge if you were in the ICU. On March 26th, original model, all the way through to April 2nd, we assumed that was 8 days. Now, given data we have that it takes a long time in ICU, we say it's 20 days. That's 2.5 times longer. That's not 100%. That's not 200%. That's a 250% change in a key parameter of the model. Now, on the other hand, and this is the ICU stay, if you didn't get put in the ICU, we used to think you were going to be in there for 15 days, but now it's 8 days. We've cut it in half. So there's a doubling here and a halving there. What's a couple doublings between friends? And then they show some of their current data, and this is where they show some, look, there's some things have changed a little bit at the state level. So what we're looking at is the March 26th, April 2nd, April 5th, 3 models. So on March 26th, we thought the deaths per day would peak in Colorado at 20 in May, but maybe go up to 40. And then on the 2nd, we think it's going to peak at 30, which is more than 20, but earlier in April with a lot of uncertainty. And now we think it's going to peak at, it's already peaked at 20 and is going down. So they argue it's okay because their shaded areas of uncertainty overlap each other. Yeah, they do a little bit, but first week of May is way different from an already peaked in the first week of April, and an estimate of 20 is different from an estimate of 30. Whatever, what's 50%? Nothing. Now, here's New York. On March 26th, they said we're going to see 500 deaths at the peak per day. And they said our uncertainty ranges from 500 to maybe, 1,300. On April 2nd, they said, New York's in a mess. We're going to say 800 deaths per day. That's a lot bigger, but it's still probably going to top out at 1,000. And now, 3 days later, we predict it's going to top out at 1,000. Which was up here at the very top of their range, and it might go as high as 3,000 per day. So the entirety of their first 2 models is under the current observed, or nearly currently observed, death rate in New York, and now they believe it could be as high as 3,000 instead of 500. So in the period of a week, we've got a 6-fold change in the predicted daily death rate in New York. And it gets worse. Here's New Jersey. Apparently, and if you've been watching my channel, you notice this, New Jersey actually has a lot of cases. The whole northeastern corridor from Philly through New Jersey, the Guyland, New York City, Connecticut, up into Massachusetts has been a mess. And so there were some important differences. So on March 26th, Jersey's going to have 200 people that die. It's a small state, not many people are going to die. Wait a minute, it's probably going to be 300, we think, on April 2nd. And on April 5th, wait a minute, we've changed the scale now. This is now 2,000, and it used to be 400. So now we're predicting 800 deaths, which was like way up out of their range here, right? So their entire red best guess now is outside of the entire range of their gray things, and now the uncertainty suggests you could have as many as 1,000 or 2,000 per day when they had said just 3 days prior max tops 500. So if we're looking at ventilator use in ICU beds and we think 500 per day is going to be our really worst day, and then someone comes back and says, well, it's probably going to be closer to 1,000, but maybe 3,000, what good is that for planning? It's not. All right, so I've ranted at you a little bit about some of what they've said, and now I'm going to show you even more stuff because I can't help myself. Okay, so here we come. Now, I used a model a couple days ago where I just modeled the exponential growth of deaths. I didn't model it by state, I didn't model it by ICUs, and I used only a little bit of data, and my prediction ended up being low. It started out being pretty good, and after 3 days of prediction, it was low. That is, today's death rate is lower than my confidence interval by a little bit. Now, this is their April 5th model. Today is April 7th. Well, it's getting into the 8th. They predicted on April 7th there would be 14,678 deaths with a confidence interval of 13,000 to 16,900. So this is their prediction from April 7th, 2 days after the model was made. This is today's data. The number of deaths as of the end of today, according to the New York Times, is 12,943. It's below 13,000. So it's underneath their confidence envelope. Now, you might not think 14,000 and 12,900 are not that far apart, and they're not. But this is the easiest possible thing to do, is to predict what's going to happen 1 or 2 days in the future, and they missed. So we should be worried about that. Okay, switch to my table. So I have in this table, from the downloading their predictions and their data, the predictions state by state. Now I'm going to point out some places where things got different. First, I want to orient you to this. The column over here is the estimates on the 5th of April. These are the estimates on the 2nd of April, 3 days later. These are the states. And these lower and upper bounds are the error bars they're putting around their current estimates. You'll see some things in green where things have gotten better, and some things in red where things have gotten worse. Let's start with Connecticut. On April 2nd, a couple of days ago, they said 1,144 people were going to die through the first wave. Now their estimate is 5,474. So that's, about a 5-fold increase, 500%. And their uncertainty bar is from 2,300 to 10,200. Could go higher than 5,000. This entire uncertainty range is nowhere near what their estimate was 3 days ago. Now, Florida is 7,000 versus 7,000, but the estimate now has some uncertainty that ranges from 3,000 to almost 12,000. That one's interesting just because the uncertainty is so pronounced. Idaho, they thought there'd be 400 deaths in Idaho. Now they think 69. Their top number now, 102. Now, Idaho is a small place. No, it's a big place, but it's got a small number of individuals relative to other populations in the states. But that's still 400 to 70. That's 5 or 6-fold decrease. So we're getting 5-fold ups and downs. This is Massachusetts, Northeast Corridor. They predicted 2,400, now 8,000, with a range that goes up to 15,000. Maryland's estimate from 1,700 to 2,300 didn't change much, but they still think it could be highly variable. Jersey went from 2,000 to 10,000. Now, if you're planning for hospital use or even for temporary morgue space, 2,000 total deaths and 10,000 total deaths are not in the same ballpark. North Carolina, on the other hand, is going to drop from 1,500 to 500, a 3-fold decrease. 259 in Rhode Island to 1,000. Rhode Island unfortunately got clipped by the Northeast Corridor wave, and so they've done very, very badly. Texas, though, a big state where they predicted 6,000 deaths, they now think there's only going to be 2,000. So now you may say, Doug, look, you probably went through and cherry-picked all the really bad ones and left all the good ones for someone else to find. Oh, here's California. They predicted 5,000 deaths. Now they're predicting 2,000. I'm going to say to you, no, I don't do that. I'm going to show you all the data because, well, I love you and I want you to know the truth. So this is a scatter plot of the deaths predicted on April 2nd and April 5th. So the scale goes from 0 to 20,000 total deaths, and the states are labeled by their two-digit code, the postal code essentially. If they were exactly the same, you would have them on a one-to-one line right here. Let me actually do that. So being the same means being right on that line, because 10,000 then is 10,000 now. So Florida, they predicted 7,000 in their first model and about 7,000 in the new model. It hasn't changed much. New York, they predicted 17,000. Now they're predicting 16,000. It hasn't changed much. But there's some things way off the line. Jersey, they predicted 2,000, now 9,000. Texas, they predicted 3,000. They predicted 8,000, now 3,000. So things down here, they over-predicted early, and they've adjusted it downward. California and Texas are going to do dramatically better than they had thought 3 days earlier. Massachusetts, New Jersey, and Connecticut are going to do dramatically worse. Now, when we describe the relationship between the two variables in statistics, we often use the R squared. It's a coefficient of determination. It's how much information in Y can you explain with the linear relationship you observe in X. So it's a measure of, it goes from 0 to 100%. 100% means they would all line up perfectly on a line. Every one of them is exactly the same. 0 means it's like a shotgun. There's just no predictability at all. For a model to be good, if you're using it in this sort of purpose, you'd want 60, 70, 80% R squared. You'd want the models to be consistent enough that the states that were high before tended to be high again, even if you tweak the numbers, and the low ones tended to be tweaked. Well, the R squared is 57% if you include New York. But New York is a really big outlier, and we know that that influences the calculations. If we take New York out of it and we zoom in, this is what we're getting. Now, again, I'll just draw in the one-to-one line because I was careful with my axes. There we go. Right? So how many states line up on the we got it right both times line? Well, we've got Colorado, where I used to predict 2,000 deaths, now I'm predicting 300, and Kentucky, where I used to predict 800, and now I predict 1,600. So we're getting 2- and 3-fold differences all over the place in these medium-sized states. And in fact, I went even further and looked at only states under, I used the wrong graphic, drats, but in this little box right here, again, I'll do this in real time because I think I should. What am I doing? I'm doing this. Yeah, there we go. So in this box right here, all right, and I'm going to do this and do that and do that. And oh, I better make it so you can see what I'm doing. I went just into that box. And so these are the smaller ones. Maybe all this uncertainty that I'm seeing, I'm getting really rude and I'm just picking on these ones way out here that are obvious. Well, if we look inside of here, the correlation, the R squared, sorry, the coefficient of determination isn't even 22%, it's 19%. So the coefficient of non-determination is the opposite. It's how much disagreement is there between the two models. And the answer is about 80%. So they have a shared sort of predictive correlation, description, something that's quite small. They're dramatically different. Okay, so that means the states differ. The states differ by 3, 4, 5-fold. The error bars can go from 1,000 to 5,000 for a single state. What kind of planning tool are we using here? If 3 days ago I said Jersey was going to have 2,000 deaths, and now I think 10,000, but maybe as much as 20,000. So, in the press release on April 5th, Christopher Murray said, we have a massive infusion of new data. And in their FAQs, they still sell this as, our model is designed to be a planning tool. It's informed by the shape of the COVID outbreaks, and therefore it can be used to help the planning needs of hospital administrators and local governments. If we had followed their April 2nd model, we would have positioned a lot of things in exactly the wrong place. They also did say they would publish online their technical appendices. Today, it's not there. Again, remember, this is installment 3, The Search for Spock. And Anthony Fauci plays the younger Spock, although here he's, yeah, I think that's fine. We'll just leave it at that. He's quoted for a lot of things. One of the things he can say is you can't rush the science, but when the science points you in the right direction, then you start rushing. Well, I believe fundamentally That the IHME model, they rushed the science. It's based on scant data. It's based on models that are unstable. And it's based on, and you can see that in the instability of the model between iterations that are only 3 days apart. But they're still doing press releases. They're still doing the press tour. They're still arguing that this is a predictive model that can be used for planning. To me, that's irresponsible. You need to tell people, well, at the state level, our models are shit because we can be off by a factor of 5, and in 3 days we might change our mind again. Now, maybe this model is right and it's stabilized and it was just Wuhan was weird, and now we've got some more data, and maybe everything from now on is perfect. And if that's the case, that's great, right? But they put a lot of positive spin on the April 2nd model and the April 1st model. They did 5 press releases between March 26th and April 2nd. And in them, they spoke very highly of their model and its predictive capabilities, and they didn't talk about uncertainty. They did show some uncertainty. It turns out those uncertainty bounds were way off. So if we couldn't trust their model 3 days ago, and they told us it was stable and predictive, should we trust them now that it's stable and predictive? And I think the answer is no, you've lost your credibility. You have an unpublished manuscript that has not been peer-reviewed. You've made predictions that are wildly inaccurate. Or I can't know if they're inaccurate or not. They can't both be right. You can't have 2,000 deaths and 10,000 deaths in Jersey. And if you make those 2 different predictions 3 days apart, that's not one model, that's 2 different models. So all models are wrong. Some models are useful. I have yet to see any indication that this model is useful. I call it like I see it.